Let's take a look at this problem. Airplane flies at an altitude of y is equal to 10. Um, flies an altitude of 10 miles. Oh, altitude of 10 miles toward a point directly over an observer. Okay, so let's draw this. So we got our observer here. Pen's acting a little funny. There we go. And we got our plane right here. And it tells us that it's 10 miles up. So distance here is 10 miles. And draw this over here. This is the ground. I had to Google this morning. I don't remember this. I wasn't sure what the angle of elevation was. But from the pictures on Google, they show somebody standing down here looking up. So that's the angle of elevation. Okay. Toward a point directly over an observer. The speed of the plane is 700 miles per hour. So the rate of the plane, I'm trying to think of the correct word to use here. The change in distance, d for distance, with respect to time is 700 miles per hour, so per 1 hour. Okay, should have maybe did that a little bit better. Okay, for 1 hour instead of having to connect with the smiley face. It has nothing to do with that. I was just writing over on the side. I did big D for distance, so it wouldn't be two little d's here. Okay. And find the rates at which the angle of elevation is changing. So what they're wanting, and we'll call this theta. They're wanting to know this what right here. How much is theta changing in respect to time? Which changing from the angle is 30, 60, 70. Okay. Well, this is the height, and this is our distance. This would be big D. Um, Again, this is going along, and as it's going 700 miles per hour, then this is what's being reflected. Now, we got theta here. This side over here would be the opposite side, and this side over here would be the adjacent. So I got a formula for that. Tangent theta is equal to opposite over adjacent. Well, opposite is 10, and adjacent is on D. That's our distance. Okay, well, if I write this over here, we got tangent theta is equal to 10d to the negative 1, because that's like d to the first, and you can take it up on top and it becomes d to the negative 1. And we want to take the derivative of both sides with respect to time. The reason why I say respect to time is because that's where they gave us. So I want to take the derivative of tangent theta with respect to time, and I want to take the derivative of 10d to the negative 1 with respect to time. Now, derivative of tangent is, I believe, secant squared. I don't got my calc book here. But we're taking a derivative with respect to t, and this is really theta. So we have to add on, let me think about this for a second. We have to add on d theta dt. So again, if you're taking a derivative, you take derivatives just like normal, but then you put the derivative of whatever variables here with respect to time. Over on this side, we take the derivative just like normal, so take negative 1, put it out in front. lower my power by 1, so it becomes a negative 2. But we were taking a derivative with respect to t, and this is really a d. So we're going to multiply it times the derivative with respect to d with respect to, or derivative of d with respect to time. Okay. This is what we're trying to find. So I'm going to want to get it by itself, but let's do a little bit of simplifying first. So I got secant squared theta, d theta dt. Over here, a negative 1 times 10 is negative 10. And then I'll take that d to the negative 2 to the denominator. It becomes d to the positive 2. Times this right here. Now, that right there, derivative of d with respect to t, they give that to us, 700 miles per hour. So I could put that in there, 700 miles per 1 hour. I'm not very good with the units of measure, so you'll probably have to double check me. And then we'll multiply both sides by 1 over secant squared. So I'll take 1 over secant squared theta times secant squared theta times d theta dt. And if I multiply those together, negative 10 times 700 is negative 7,000 miles over d squared times 1 d squared, and I'll go ahead and put an hour here, times 1 over secant squared. Secant squareds cancel. And you got d theta dt is equal to this. Okay. Well, we're given theta. They ask us the different values of theta. 30, 60, 70. And we're not given d, though. I had to think about that for a minute. If we have, this is, let's say, 30 degrees, our first one. If we have, this is 10, and we don't know d in this case, this is opposite over adjacent, so we'd have tangent of our angle is equal to the opposite side, which is 10, over the adjacent side, which is d. And then I could solve this for d, and that would give us this value here. We plug in our theta, and assuming I don't have the units of measure messed up, then that'll give us the rate of change. So hopefully that helps you. Unfortunately, I'm not that great at word problems, but maybe if nothing else, that'll give you a little bit of an idea of where to head with that. And again, that's assuming that my Google definition of angle of elevation is correct. If the angle of elevation was up here, then it would be slightly different. You know, the opposite is here, and the adjacent would be here.